Hey class, happy Saturday. Hope that y'all are doing well. As you can see, Meerkat has stolen my chair again. I told you she does this all the time, and I'm too weak to kick her out, so just have another chair here instead of kicking her out. Anyway, we are here to talk about risk. So, the distinction that we make between risk and uncertainty more generally is just that risk has some negative connotation attached to it. We're thinking about a chance of experiencing some loss or negative impact. There are a lot of different frameworks for how to mathematically calculate risk. This is just one of them. It's one that I use in my research, but there are many others. The way that I think about risk is these three parts. We can break it up into threat or hazard, which is the probability of some event occurring which could cause that harm. Vulnerability, which is the probability distribution of impacts that could be caused by that event if it does occur. And then the consequences, which are the value metrics associated with the impacts of an event. Mathematically then, our quantitative definition of risk is the product of the lost value that could occur and the probability of it happening. So our risk is divided up into these three parts that we're going to multiply together, where first we have the probability of the event of interest X occurring times the probability of different levels of vulnerability, V, conditional upon X occurring, and then multiplied by the loss function that tells you how much damage occurs or what is the negative value metric associated with a given level of vulnerability. If we look at my own research, I do a lot of work on flood risk that I've talked about before. And so a simple example of this would be if we're thinking about a single storm or a single hurricane hitting Louisiana. We would define our storm event as S, and we have some probability of observing a hurricane. And then we have a certain probability distribution of flood depth that that hurricane could cause. So we have our probability that D sub F, the flood depth, equal a certain value conditional upon storm S hitting. And then we have a loss function, which for me would be the damage that is caused by a certain level of flooding. That could vary depending on what my spatial unit is. Am I thinking about the damage to a particular house, or am I thinking about damage to the entire Louisiana coast? And the damage might come from a variety of different categories. We could talk about structural damage or damage to the contents of the house. We could talk about the extra cost of having to relocate and potentially live in a hotel somewhere else while we're reconstructing or repairing the house, and so on. But we could add all of those up to generate a loss function that describes what's the direct economic impact as a function of the flood depths. You may be thinking, why do we separate the hazard from the vulnerability? We have these two different probabilities that we're multiplying together, but why don't we combine those into a single probability that's unconditional on the storm occurring or the event of interest? In the flood risk example, it's one thing to be able to estimate the probability of a hurricane forming in the Atlantic Ocean or Gulf of Mexico, and then it's another to be able to estimate or model how much storm surge and flooding is going to be caused by the storm if it does occur. Estimating the likelihood of a certain storm occurring is more the domain of climatologists and meteorologists, whereas estimating how much flooding is going to occur if that storm forms is more of a fluid dynamics question. So we would have different models that are used to estimate those two quantities, so it's convenient to keep them separate in our risk framework. Most importantly, for engineering applications, we might not be able to actually have any impact on the underlying hazard, but we can develop solutions that reduce the vulnerability or the loss. There's not a whole lot that we can do to prevent a hurricane from forming, even though Scientists have tried in the past. There are all sorts of experiments about seeding clouds or other ways that we can try and break up a hurricane when it's still forming out in the ocean, but they haven't been very successful. So there's not a lot that we can do about the underlying hazard in this case, whereas we can build a levee or a flood wall or elevate someone's house so that it's not going to either receive flooding in its area if there's a flood wall in front of it, or it wouldn't take as much damage if it's elevated off the ground. It doesn't make a whole lot of sense to talk about the risk associated with just one specific hurricane because there are lots of different kinds of storms that could occur. We have a category 1, 2, 3, 4, 5. Hurricane Katrina that hit in 2005 was very different in its characteristics than, say, Hurricane Isaac that hit in 2012. They took very different paths. One was much larger than the other. One was more intense. One produced a lot more rainfall. The other produced a lot more storm surge. So there are lots of different factors that are going to influence the flood depths that occur as a result of a given storm. And lots of different types of storms could occur. So we need a way to aggregate all of that risk in order to calculate an expected value for the economic losses that could occur. Basically, what we're doing is using the law of total probability to sum up over all the types of outcomes that we could see and all of the outcome measures that are associated with that. So if we have a decision metric M, start out by enumerating all the different events X that could occur. Then we need to calculate the metric's value, M of X, or the probability distribution of values associated with each event. If the events are discrete, sum up the metric values over all of the events, weighting by the probability of each event. If we're continuous, integrate the product of the metric value function and the events PDF over the event space, and then apply the decision rule using the expected value of that metric if we are in a risk-neutral situation. Here's an example problem where you can test your understanding of these concepts. Take a few minutes, read over the problem, and try and actually work it out for yourself. You can either do this one on pen and paper, or you could build a little spreadsheet model for it. I'll show you how I would tackle it in Excel, but first, try and do it yourself. To simplify the problem, we're going to look at only 3 possible outcomes for the number of days of good skiing weather per year that we will see going into the future. We also have different assumptions about the value that we're going to get per day, depending on how many good days of weather there are. So we need to carefully think about that as well. We're told that the owners want to recover their initial investment within 5 years and have an annual rate of return of at least 25%. There are a couple of different ways that we can approach this problem, but either way, we're going to use a 5-year planning horizon, and we could set a hurdle rate of 25% per year if we want to calculate the present worth of the project. The other way that we could approach this would be to calculate the actual rate of return and see whether or not it's greater than or less than 25% per year. Here's all the information from the problem laid out in Excel so that we can calculate the revenue and expenses associated with each possible outcome. If we think about mapping this onto our 3-part risk framework, it doesn't map exactly because we're going to generate revenue no matter what happens. But we can still break this up into 3 different components. First, we have the event itself of how many days of good skiing weather are there going to be per year. Next, we have the impact of that in terms of the number of users of the ski lift per day. And then finally, we have the value associated with that impact in terms of the profit that we would make. That means that first, we need to calculate the value metric for the profit we would generate under each of the 3 outcomes. To do that, we need to calculate our revenue and our expenses. The expenses are straightforward. We have a fixed daily expense of $1,500 per day that the ski lift is operating. The revenue is a little bit more complicated based on the problem statement. If we have 80 days of good skiing weather, then it's easy. We just take the number of users per day multiply it by the number of days and the price of the ticket that each person is going to pay. However, we were told in the problem that if we get more than 80 days of good weather, then on the last 20 days of the season, fewer people are going to be using it. However, on the first 80 days, we'll have the same revenue as before. So the way that I have this set up is we take the revenue from the first 80 days, calculated on the previous row, and then add in the number of users in the last 20 days multiplied by the difference between the number of days, so that's D3 minus D2, or 20 days of extra good skiing weather, times the ticket price. We have a similar calculation if we end up with 120 days, where we can take the revenue from the first 100 and then calculate the revenue from the last 20. As always, I'll post this on Blackboard so you can look at the formulas in more detail and play around with how it works. Ultimately, though, that allows us to take the difference between revenue and expenses to calculate the profit depending on how many days of good weather we have. Then, using the law of total probability, we need to take the profit from each outcome, multiply it by its probability, and then add that up to create our weighted average of the expected value for the annual profit. I'm using a formula in Excel called sum product that does basically exactly what it sounds like. It's going to take the product of two different columns or rows, depending on how you specify it. In this case, the column of profits and the column for their probabilities. It'll take the product of those cell by cell, so the vectors have to be the same length, and then it'll add them up, take the sum. That allows me to calculate an expected annual profit of $303,000. Now we can look at a number of different ways of solving the problem once we know that expected value for the annual profit. Here on the right, I've calculated year by year the cash flows associated with the project, where we have an initial investment at t equals 0, and then an expected value for the annual profit in each future year. If we want to calculate the net present worth of the project, we can take a hurdle rate of 25%, calculate a p given a factor, and then total up my cash flows using the negative initial investment and then 5 years of an annuity equal to the expected annual profit. So I take this $303,000, I multiply it by my p given a, and then I subtract my initial investment of $900,000. That gives me a net present worth of $85,148 in the whole. So we have a negative present worth in this case. So we would say that this project is not worthwhile. Alternatively, now that I have a column with all of my cash flows in it, I can use the IRR function in order to calculate what the rate of return actually is on an annual basis, and I get 20.31%. That's less than the 25% that the owners demand. So again, using another decision rule, we get the same answer. It's not justified. Finally, the last way that we could solve this problem would be to actually calculate the break-even time, assuming that we could continue to receive that $303,000 in expected annual profit, even beyond the planning horizon. To find this out, I'm going to use goal-seek under the what if analysis in the data menu. And what I want to do is set the net present worth of the project to 0 by changing n, the number of years. That'll give me the break-even payback period, essentially. And what we get is 6.08 years. That's more than the 5 years that the investors want to get their money back in. And so again, the payback period longer than what they demand, therefore it's not justified. In the next video, we'll go back to the case study example from the very first day of class, examining the decision made by the Port of LA on whether or not they should harden their terminals against extreme levels of sea level rise. Thanks for watching.